Li from Lambda Group of Nanjing University, the same group as our third presenter. Today I'm going to talk about continual multi-objective reinforcement learning. As we know, in the classic reinforcement learning setting, our agent learns to complete one specific objective by maximizing a scalar return. For example, the agent in the Pong and Atari games learns to maximize the score points to win the game, and the agent controlling the hopper in Mojogo tasks maximizes the reward to learn to move in the forward direction. However, in some scenarios, there may exist multiple or even conflicting objectives. Like, for example, for an autonomous driving agent, one objective is to drive fast and another objective is to drive smoothly. Both objectives are important, but they may be conflicting. And for the agent, during testing, it needs to make decisions according to our users' preferences, overall objectives. For example, for a busy businessman, he may prefer the agents to drive fast, but for leisurely travelers like us, traveling in the beautiful Jeju, we may prefer to drive smoothly. And in this setting, we cannot apply the traditional RL algorithm to find one single optimal policy. Instead, multi-objective reinforcement learning aims to find a set of policies that approximate the optimal Pareto front, as introduced by our second presenter. And the majority of current MRL methods aim to find a better front, including multiple network methods, single network methods, meta-learning methods, and the one introduced by our second presenter. I'll skip this part to save some time. And in all these methods, the agent trains and tests on a fixed set of objectives. However, in some real-world scenarios, our agent may deal with some human users who may propose new objectives at any time. For example, after one day of driving, our passenger user may propose a new objective, like staying in the lane. And another problem is that the reward signals for some objectives may become inaccessible due to some detector or sensor malfunctioning, but these objectives still matter. And in conclusion, the learning objective set for the agent may evolve over time. We formalize this problem as the continual multi-objective reinforcement learning problem. And the agent learns in a continual manner, and the objective set, in the past, the agent learns about this objective set. And at the present, the set may change to this one. It may change to this one, and the agent needs to learn about it. And in the future, this set may change again. So to solve the problem, our agent first needs to learn about the new objectives very quick. And instead of training the entire agent model from scratch for the new set of objectives, we designed an expandable network architecture and when new objectives arrive, our agent simply expand the agent network in the red ones to learn about a new objective. And for objectives lacking reward signals, the agent needs to retain the ability to achieve those objectives. So we propose the Reward Model Rehearsal technique, which learns a multi-objective reward model to simply recover lost rewards, so the agent can learn over all encountered objectives. And we prove that the performance gap between this technique and the settings where the agents have access to all ground truth rewards is bounded by the reward prediction error, which can be reduced with model learning techniques. So here is an overall learning procedure of our method. And as the time changes, our agent expands its network, trains the reward model, and uses it to recover the lost rewards. And the agent can learn all encountered objectives using the existing MRI methods. To evaluate if our method can really solve the problem, we first design a task that the objective set changes from AB to BC, and we compare our method to a baseline that learns from BC from scratch. So So this baseline learns the objective, the parental front from here to here, and our method learns both objectives much better. It learns fast to new multi-objective tasks. And the second experiment is that we design the task same, AB to BC, and we compare our method to the fine-tuning baseline, which directly fine-tunes the entire agent model on the second objective set BC. And unfortunately, it encounters the catastrophic forgetting phenomenon. It forgets how to complete the original, the old objective A, so it moves to the left side. And our method remembers the old objectives and even keeps improving it. And finally, our method achieves the best overall performance. In conclusion, we proposed, our main contribution is to propose the continual multi-objective reinforcement learning problem and try to solve it. And in the future, we may apply this work to the human-AI coordination problem because this setting naturally fits the need in this problem because our agent need to deal with multiple people having different preferences. And yeah, we may apply this work to this problem. And that's all. And thanks for listening. I will be happy to take questions. These are my contact info, and welcome to discuss with me at the poster. My poster is just next to the elevator. Thanks. Thank you so much.
Thank you for coming up. Thank you so much. Definitely go talk. Seems like really cool work.
Thanks so much.